Okay. How's everyone doing? Doing okay? All right, I'm glad to hear that. Welcome. Welcome, everybody. How's it going? All right. Thanks for being here today. Yeah, so why is it going so well? What's that?
Easy homework.
Easy homework. All right. Well, I'm glad that is what you need. That's good. Why else is it going well?
It's almost Friday.
It's almost Friday. Okay, great. Yeah. So, are there any administrative questions? Hopefully the APDL was not exhausting. Okay. Now you can put on your resume, I have used APDL. Right. Yeah, are there any other administrative questions? You have something else due tonight, right? Right, so are there any questions about groups for the final project? Yes.
On the form, you say dimensions. What does that mean?
So it means what size, or are you doing 2D? Are you doing 3D? That makes sense?
So basically just 2D or 3D?
Or you can say, I'm going to get, my object that I plan to simulate is on the order of a meter. Okay, in length. Right, so that's what we're getting. All right, other good questions. Yes, and your name again is?
Jesse.
Jesse, yes.
So if we submit the pre-proposal, does each person have to separately submit it? And if so, does it have to be different?
No, so, okay, good question, Jesse. So every single person should submit the pre-proposal. Okay. And then you can have the same exact responses. And I hope in most cases that also the pure evaluation portion has the same exact responses. But I understand that, whatever. So, that's where, it is still a private submission, I guess I'll say. Does that make sense? What we're going to do, we're going to talk a little bit about the final project in a little bit of detail in just a minute. We are going to have another assignment due next week, which is the preliminary outline. Okay. And what I'm going to try to do, per suggestion of the TA, one of the TAs, and it makes sense, is once I have your groups set, then I will create groups in Canvas. So when you have your outline, that you'll be able to submit one assignment moving forward. Because we realized, or the TA realized, that it's a pain when we're looking at 3 different outlines. There will still be the opportunity to comment on the distribution of contributions, okay, here going forward. Okay, so what essentially happens is, we assess what you submitted, get a grade, and then, if everyone submits, or everyone says they did an equal contribution, you all get the same grade. If not, then grades will scale. Okay. Any questions on that? Yes, Josh.
This is something different. I see that we have sometimes assignments for guest faculty lecturers. I suppose last week wasn't really a faculty lecture, but do we have to do an assignment otherwise for that?
No. So for Chris Sakalaris' presentation, the only thing is the attendance, if you were in Group A, and the screenshots essentially for the APDL exam. Okay. Any other questions? Great. Okay. Yes, Cameron.
Will there be any penalties for the distribution?
For the what?
Will there be any penalties for if your one teammate maybe less than 10, more than 10?
I'll look at things, typically what happens is two people kind of agree on the distribution, right? Even a third person often agrees with the distribution. Like people will adopt themselves, okay? Like they'll just be honest. So, so yeah, it does affect the scores that everyone receives. Okay. If we need to talk about things, we can. Right? How many members of a group in each group? Okay. Thank you. Right. It seems to be the right number for distribution of work, for the size of the project, and yeah, no one, everyone has to contribute. Okay. Good. And of course, if you want to do a group project with someone in group B, you're welcome to do that. There's nothing, you don't have to be, same group A or group B, right? You can be groups. Okay. Well, let's talk just a little bit about outlines, and then we'll get into fluid mechanics, and then we'll talk about the finite volume method. Okay. So this outline this screenshot is the outline that you will be attacking in a Word template. Okay, so what's going to happen is I'm going to give you the template, which I give you, right? And I'll sign it. Everyone can copy it. I do want each team to have one Word template. Okay, and we're going to keep track of that. Like once you've set this thing, this is essentially the assignment. I mean, you're going to be using that same link for the rest of the semester. Okay. So the preliminary outline is not going to have material in every one of these sections. Okay? You haven't done it yet. Okay, but I'll have a little bit, and you can watch a video or two. You can read a short paper about how to go about using outlines for research. The goal is essentially to help us write a short paper that might be a short article for a journal or a conference. Okay, so the idea is to kind of introduce, and Professor Singer's the one that started this. I have a slightly different template than he does for these types of articles. The idea, though, is the same, that we get to work on communicating and organizing a research project. So we want to have an idea of what we're doing, and the objective, often, I don't expect anyone to break new grounds on science in the next few weeks. If you do, that would be wonderful. Okay. Often, though, the objective for an academic journal article attempts to explain what is new about what we're trying to understand, or what is ongoing. Okay. What is the question, the kind of larger question that we're trying to understand? How does current work fit into that? You can share your most important results, and you can also explain who cares. Then we get into the introduction, which is what is the problem we are trying to solve. Again, also what is new about that problem, but this has a slightly smaller has a smaller scope than what our objective might be. Okay, so for example, the objective might be, hey, we're trying to understand the role of turbulence about airfoil in affecting liquid travel. Okay? Whereas the problem that we're trying to solve might be something more specific, like we are trying to calculate the liquid drag ratio of an airfoil of a 2020 or a 2412, a NACA 2412 airfoil with angles of attack ranging from -2 degrees to 2 degrees, right? Nowhere close to stall. Okay? So that's kind of the problem that you're trying to address in your study. Okay, and you can you elaborate a little bit more. You repeat yourself in the introduction. So you have an abstract and you also repeat yourself, okay, when you get to the introduction. And you talk about the motivation and the background, all right? Really, there should be a hypothesis, okay, embedded in here, okay? And we've talked about hypotheses a little bit in the past. The word I like is depends, okay? But it could be conditional if, then, okay? And you're going to attempt to test that hypothesis. In this case, they could be a little bit of a throwaway, okay? In terms of, again, we don't expect to be breaking new science here, right? You can say the transition to turbulent flow depends on the Reynolds number, and it varies by 20% or something like that. Like that could be your hypothesis. Okay? So if the Reynolds number is this, then we hypothesize that. Okay? So that's kind of an idea for a hypothesis. And so, yes, please start putting that in there. The methods in experimental design. Yes, you're like, wait, am I really doing an experiment? I want you to think like an experimentalist if you can. Okay. With what we're doing with ANSYS, it's not, it's not building hardware, but it's trying to build a very simplified version of hardware that you can then run calculations to see how it responds. Okay. And you can describe the simplifications and the geometry that we're using. Okay, we're going to have a lot of fun. Okay, as we go on, there will be checkpoints. And well, this is not exactly the same thing. This is a check, but at one point, right? So you're submitting this preliminary, and then you're going to submit an initial simulation, just kind of showing, hey, I can actually simulate something. And then you're going to submit a checkpoint on convergence, right? And we now, by this point, right, we probably almost exhausted the number of times we have to show convergence. Okay, and so if you have time dependence, right, you might look at the time step. You have geometry, right? With dependence on geometry, you might look at changing the mesh slides. Okay, so we want to use those principles, those ideas to show that we can at least get to some local minima on our results. You also have to, of course, choose a metric. So maybe you're going to choose velocity as a metric, or whatever it is, or a temperature. Okay? That you're going to take that metric, and that's what you're going to look at to see if you're getting to convergence by changing the size, the time steps, and the size of the mesh. There will be images. There will be graphs, preferably in MATLAB, produced by MATLAB, or some other nice software. The screenshots that you include, okay, should really only be of the finite element results. Okay. The actual, if you're plotting this versus that, okay, and we understand if you can have a table that lists, your parameters and the values that you might put in, but please do not show me a table of your design points and copy and paste that into your final report. Okay, that is not what we're going for. Okay? Even at this point, you know how to take that data, put it into a MATLAB file. Okay? You'll be doing some explanation. There will be a rubric that we have here. Professor Singer weighed very heavily the discussion portion of the paper. He wants to see how you're thinking. He had a separate section for results. I put results and discussion together, so it's a little, I guess, more, it's a little, maybe it's more nebulous in terms of what we're going for here. That said, I do want to see that you discuss and you show that you have some understanding, and of course you bring it back to your hypothesis, right? So in your explanations, you're going to bring it back to your hypothesis. Okay. And then you'll conclude, and you need to have references. Okay, a note on references. Please use a reference manager. Okay, and you're going to be using Microsoft Word. Okay, so anyone know what a reference manager is? Anyone have a favorite reference manager? Anyone used one before? Yes, Mia. Huh? Okay. All right. So there's one. What are some other ones? So I'm not familiar with that one, to be honest. Okay. Does it allow you to put a citation and then create a separate works cited at the bottom? Okay, that one's appropriate then. Okay. So please use one. I like Zotero. Okay. Zotero is pretty nice. Rogers has licenses to RefWorks and also has licenses for EndNote. Does anyone use EndNote anymore? Wow. Okay. Yes. Yeah, I think that's Evernote. Yes. Yeah. Right. Not so. So anyway, so you have options for your reference manager. Please put them in a reasonably good format. Okay. My suggestion: IEEE format. Okay. This is a nice format for your references. It uses numbers in the text. Okay, like like that, and it puts them in a nice looking format in the reference. So that would be my suggestion. In the past, I've required Zotero. I'm not going to require this. Okay, so use what you want to use, but use something that all of you can use. So you should have, essentially one database of all your references. How many references do you think you should have? And what kind of references should they be? Yes?
In terms of what kind of references they should be like other academic papers that address the topics we're talking about.
Right, so they can't, they should be probably, okay? There should be at least 5. Okay? And you need to have, I'd say, at least, well, let's say 3 should be academic articles. Okay? And it's not hard to find an academic article. Okay? And I don't know how this easy bin works, but Zotero, if you install the extension in your web browser, you just click and it creates it when you're on the page for the article, and you're done. You can cite books if you find values or other examples. Okay. If you're using a tutorial, you can't read that, can you? YouTube, ANSYS, whatever, please cite. Big time. Okay? I've seen a few of these papers now. Okay? So just cite them. I'm not going to dock you, all right? And make sure that what you're doing is within, let's put it this way, the level of this course, right? If like suddenly stuff is coming out that looks way beyond what I think you can do in a few weeks, and you have no citations, it's not going to be pretty. Okay? So please just cite. Please, please, please. Okay, any questions? You don't have to put any references in your paper, in your preliminary proposal next week. Okay, Okay, this is as we go forward, we're talking about, you know, what the outline should look like. When will you transition from outline to final report? When will you get rid of the bullets? When you submit the final report. Okay, so there should be bullets in all your submissions until the end. Then they can go away. Any questions on that? All right, good. So, just and I'll have this thing is going to be due next Thursday. Well, okay, I have to take a look. That would only would be a couple of days. Okay, so it might be due a week from Tuesday. I gotta see. I gotta look. I'm a little behind here, but this is what we want. These are a few more details in the preliminary outline, and so you can have like just a few sentences, but please put them under bullets. Okay, for the introduction, results of discussion. Okay, what is one baby step benchmark? So, for example, if you're going to do an airfoil, right, and you want to do like a morphine airfoil or something, people do airfoils. Do one that you know, you can say, hey, I got to work, because we're going to do these kinds of examples in the class, right? You can't do the exact same, you cannot do only that airfoil, but you can show that, hey, I got convergence, I trust this, I'm going to move on. Or maybe you want to do some kind of simulation with some weird shape going through a flow. Okay, I guess lots of CFD type problems we're picking up today. Do a sphere first, or do a cylinder first, which we'll also do, okay? Then try to talk to us a little bit about the geometry you're going to simulate. And I'd like to see a rough sketch, so you can put your first figure in there. And you don't need to have abstract, you don't need to have conclusions, you don't need references for the okay, so those you can do. Okay, any other questions? We're good to go? Yeah? All right. Okay, so we're going to talk about fluid mechanics someday, and we'll show you the derivation of the Navier-Stokes equations. Hopefully you have a few insights. We'll try to go to Navier-Stokes quickly, all right, so you don't, because I know you've done it before. And then we'll talk about finite volume, the finite volume. And I think you're going to like the finite volume. It's a lot more straightforward mathematically than the finite element. Okay, so let's talk about the number one thing that we often care about in fluids, which is the shear stress. Okay. I mean, we care about it in terms of being able to do the math, I guess. And but we don't exactly, we can kind of measure it in some ways, okay? And we can kind of think about how it acts in the flow, and we can think about how it interacts with the viscosity to then create stress, and how it can act over an area, which then creates, we can think of a the derivative of the flow, in one direction relative to a perpendicular direction, in fact, the shear stress. Okay, so let's spend a little bit of time doing a pretty basic example. And in this case, has anyone ever washed their hands? Okay, hopefully yes, right? And has anyone ever rubbed their hands against each other? Yes, when you wash them, right? And has anyone ever thought, there's a lot of shear stress in my hands? No? Okay, all right. So let's think about it. Okay? So this is the bottom hand. Okay? And this is the top hand. All right, we'll call this hand 1, hand 2. All right, and let's say that they're sliding against each other. Okay? And you've got essentially a film of fluid in between them. Maybe there's soap, maybe there's not. What is the profile for the velocity of the fluid between these two plates? In the global reference frame. Yes?
One fluid is moving with the left hand, one fluid is with the right hand, so it's kind of like linear.
Yeah, exactly, right? So if you draw this kind of thing, the fluid flow profile would maybe be something we describe by U, and at this side it's V naught, and at this side it's 0. Okay? Now, if we put a coordinate system in here, and we say this is the y component, and this is the x component, how would we describe du dy? Okay, so right, this is we already said we have this u. It goes along here, right? What do I need to know in order to calculate this first? Like, how would you? Right, because what we want to do, right, is we want to, we know that the shear stress is going to be the dynamic viscosity times this derivative. Okay. So what is du dy? Someone else. Maybe quadrant 1, which is kind of back there. There's quadrant 1, quadrant 2, quadrant 3, quadrant 4. Someone quadrant 1. You might need you could say, I need more information. Well, what do you think? Yes?
If you assume that it's a very thin fluid layer, so you can assume it's a linear, velocity profile, it would just be your maximum velocity at the top multiplied by wherever you are, the y coordinate, divided by the total height of the boundary layer.
Yeah, good. Okay, so let's say that this is got some distance here, g. Okay, and is the slope constant? You betcha, right? It's constant. So this is like a y equals mx plus b type problem. So what's the slope? Well, you rise up to some velocity over some gap g. So your gradient is going to be just that plate velocity divided by the gap. All right, and so another way to write this is to say this is the gradient of u. Like that. Okay. So now we know that the viscosity times is the shear stress. how would you, if you're an experimentalist, how would you go about measuring the shear stress? Maybe someone in quadrant 2. How would you go about calculating this? Yes.
Is it touching water?
Yeah. So this is, yes, this is essentially the film of liquid, and this is the ideal scenario, right? So it's not, I'm just joking about the hands. But now let's say we have 2 flat plates, and we are going to have yes, uniform liquid in between them.
I want to see how the flows.
Okay. Yeah. So that's an idea. So one way to do it would be to say, hey, what is the gradient, and what is the gradient, and what is the gap? Okay, and kind of estimate it that way. Okay. And what if you did that, and your goal was to measure to figure out what the viscosity is? Let's say we're making a simple, what's called rheometer. How would we go about measuring the viscosity of the liquid between these 2 plates? So we're imposing a velocity, and we are keeping a constant gap. What are we going to do to measure the mu? So I've got the gradient like you suggested. And what's your name? Okay, yes, quadrant, great. Someone in quadrant 3, what do you go? What would you do? How would you make a rheometer out of my hands? Yes?
You can replace shear stress with the force in the area.
Oh, yeah, that's right. Okay. So if I've got honey between my fingers or between my hands, right, and I start sliding, I know for a given gap and a given velocity, right, I know it's going to be more force. So if now we say, hey, this has some area associated with it, and I have the ability to measure the force, right? So I'm saying, oh, there's some force associated with it. Then we can say that the shear stress is just going to be that force of, we'll say, pooling over the area of the plates, the contact area between the plates and the wall. Okay, does this sound familiar? Okay, just to give you a little bit of all right, we can kind of get a sense of what viscosity is, you get a sense of what shear stress is, and we can get a sense of what the gradient looks like. So the gradient, okay, is a little bit more complicated in 3 dimensions, right? So in this case, we had, or even 2 dimensions. Okay. In this case, in 2 dimensions, our tau xy only had velocity in the x direction, so in the u direction, or the u velocity, right? There's no velocity in the vertical direction going up, from one plate to the other, and that's a pretty good assumption, especially when we say the gap is small. Okay? So in this case, the tau xy that we were measuring would have had a 0 over here because there was no change in the velocity in the vertical direction. Okay? And if we want to go to 3 dimensions, you don't have tau xyz. Okay, we know that, right? But what do you have? That from your mechanics days, your fluid mechanics days. What are your options for shear stress? Well, tau xy is one of them in 3 dimensions, Cartesian coordinates. What are your other options for components? Yes.
For 3 dimensions, tau xy, tau yc, tau mc.
Yeah, right, those are your three. And you can say, oh, tau zx, tau yx, but it's symmetric for a material, typically. Okay, so this is to give you an idea of how we can think about the different stresses in fluids. There are videos you can watch if you like that kind of help us understand viscosity. The Reynolds number. So, what is the Reynolds number? Tell us. Yes, your name? Q, yes, Q. Okay, good, right? So we can, the Reynolds number. If we have laminar, some type of transition, or turbulent flow. A couple things. So before we get to the numbers associated with these different regimes, what is it really telling us? And physically, what do they tell you in your fluid mechanics class? Someone else. Hold on. Someone else. Yes.
It's the ratio of inertial and viscous forces.
Yeah, exactly, right? So it's a ratio of, you have inertia up here, right, with the density times the velocity, right? That's kind of like a momentum, right? M times V over viscous forces. So inertial forces and viscous forces. Very well. So low Reynolds numbers mean that viscosity is dominating. So between two plates, if I'm moving pretty slowly, I'm going to have a lot of this viscous forces involved, and I'll be able to feel that. And if if I have my plates far apart from each other, and I'm going very fast, then in that case, I might be seeing some type of dominance of inertial loads. Which one of those cases do you expect to see more swirlies? When the plates are far apart, things are moving quickly. Right? That's where you see more of the swirlies. So we have an idea, going back to our simple example, of this transition between when you have laminar flow and when you have turbulent flow. And if you go really slow, you can have what they call creeping flow. And there's some advantages to doing situations, to using that. And we'll talk about that when we do flow about cylinders. And so the transition, what is kind of the rough number for when you have laminar? So laminar, transition, turbulent, and it can depend on your geometry. It can also depend on if you can avoid introducing instabilities. So if you can kind of keep things without vibration, for example, your transition regime can be much longer than if you have like a vibrating plate or something. So what are the rough numbers for like a pipe? Yes. Okay. So 4,000 is that's a rough one for where you have the onset of turbulence. Okay. And then where are you pretty certain? Where do we normally say you have laminar flow? Under what number? Yes.
2300.
Yeah, 2300 or 2000, we'll say. Okay. So this is that, you know, if you're in, and then this is transition, and then you've got essentially turbulence. When you start dealing with airfoils, they are often running at much higher Reynolds numbers than this. Okay? So you have turbulence. Okay, and if you want, you can watch The Efficient Engineer explain laminar and turbulent flow. Okay, take a break from writing, although we haven't written much yet. We'll write a little bit more in a little bit. Okay, so if you start off with some type of velocity field, you might want to take a total derivative of that velocity field with respect to time to calculate acceleration. Right? This kind of makes sense, right? F equals ma, and in some respects, the Navier-Stokes equations are really just that. You can use the chain rule on the individual components. So here's a derivative of the velocity in the x direction with respect to time. And using that chain rule, we can then take the partial of the velocity in the x direction with respect to time, and we can say the partial of the velocity in x direction with respect to x times dx dt. So that's just essentially u. We can work this all out, and this is what we get using the chain rule. This expression for these last three components is what we call the divergence operator, or the divergence of the velocity in the x direction. And we have that same old time-dependent component of the velocity. If, of course, the flow is steady, then these components in the x and the y and the z directions will go bye-bye. This is a definition of what the of how the divergence operator works, and that's just going back to what we had there. Now, we can say that the acceleration can be written in terms of this divergence operator on the velocity field. And we have this partial with respect to the velocity field with respect to time, partial of the velocity with respect to time, which is what we use to think about the local acceleration. So, and as we just said a minute ago, this vanishes, this goes to zero when we have a steady flow. Over here, we have what we think of as a convective acceleration, and it's saying that the changes in velocity that we're going to be dependent on where you are. This d dt, or the d dt with a capital D, right, can be thought of as a total derivative or a material derivative that has four terms. So what we're doing here is essentially, this was on one component of velocity in the x direction, but we've essentially come up with an expression where we have acceleration in terms of a total derivative of the velocity with respect to time, and that breaks into these two components where you have the local accelerations and you have the convective components. Now, if we go to thinking about flow through an element, like we have here, you could have a flow going through an area, which is essentially a flux. Okay? So, in this case, if I have flow in the x direction and this wall has dimensions in the vertical, and so that would be the y direction here, and then also into the void in the z direction, I can think of some type of inlet flux, okay? And I can think of some type of outlet flux, okay? And there's going to be a difference potentially between what's going in and what's coming out, okay? And so that difference can be captured not in the area, right? The cross-sectional area stays the same. That's going to be A. But the flow itself, okay, there could be a reduction or an increase in the flow. There could be a gradient across this element in the flow. And this is essentially saying, hey, you know, just going from here to here, there could be a change in that flow. Well, we can look at this as this is kind of a differential form of this, and then we can also look at an integral form of mass conservation. So in this case, what we're saying is that the control volume, okay, if that changes as a function of time, something about that morphology changes as a function of time, then it's possible that the inlet and the outlet, right, so the mass flow or the volumetric flow in this case, well, no, this would be mass flow, could change. Now, the A and the A's and the B's can change, right? Right, if you have a nozzle or something, okay, the element is not perfectly having the same cross-sectional areas at the inlet and the outlet. You can have velocities and areas that are changing, but this is if the control volume is not changing, not dynamically changing in some way, you're going to have the flow, the mass flow rate conserved. Of course, the density needs to be constant too, so that's maybe another thing to keep in mind. And that is not always the case, of course, especially with the use of the gas or air. Okay. So the differential form is that you have this divergence times the density that plus this change in the density with respect to time, right? This is the differential form. And often, since this goes to 0, then we have a continuity equation, which we write as the divergence of the velocity is just going to be equal to 0. Okay, and so that's what you see here. For an incompressible fluid, the density is not changing as a function of time, and we can take out that rho term, and so the divergence is equal to divergence of the velocity is equal to 0. Okay. Now, with this setup for conservation of mass, if we don't have that as, if we say, okay, things could change and the density could change, and we have, for example, some type of sink or some type of source or essentially a flux. Remember, this looks kind of familiar when we were doing the heat equation. Then the calculations can become more complicated. Okay. But even when the flux or the divergence of the velocity is equal to 0, we can use it. It will still help us understand that for a constrictor or some type of nozzle, we're changing cross-sectional area, the volumetric and the mass flow rates are going to be the same. And there's also an integral form that we can use to think about this flow. This kind of idea of rho v going through an area, some type of flux, is going to be very important in a few minutes when we talk about the finite volume method. So we can take what we've been doing and shelve it for a minute and think about momentum. Okay? And when we start to think about momentum, we can think about body forces that are going to be involved in this system. And so we can think of this flux momentum as described here with all these different terms in the u, the v, the w, so the x velocity, y velocity, z velocity. And we can then apply continuity and we can get an expression that says, okay, I have some type of body or surface force that's acting on my system is dependent on the dimensions of the control volume, and is dependent on this rho and this dV term. Now, dV term with respect to time. So that already kind of looks like an acceleration term, right? That's the force. So, once we look at the contribution of these body and surface forces, and we think about what's happening with a pressure differential, and we think about what's happening with gravity, we think about what's happening with the Laplacian of velocity, okay, or the divergence of the shear stresses, we can equate that to the inertial term, and we get Navier-Stokes. Okay. So the kind of in Cartesian coordinates, the common way to write this out would be where we have a so we have gravity terms, we have our hydrostatic terms, and we have our shear terms, and we have our inertial terms. All right, so and we have our x, we have our y, and our z, and so you think, okay, I have some gravity component in the x direction, I have some type of pressure, hydrostatic, okay, in the x direction, so I can think, okay, I've got, that's a p, not a rho, something like that. And then I have a contribution from the shear stresses, and so these terms are going to have viscosity, and I'm going to be interested in the second derivative with respect to x, the second derivative of, and this is for the x velocity with respect to y, and the second derivative with respect to z. And then in the inertial component, I have a rho times the acceleration in the x direction. So you can go through this for the other components as well, and voila, we have the Navier-Stokes equations. Now, how many times are we going to solve these equations by hand like you did in fluid mechanics? Not many, if any, okay? We're going to use the computer to solve these equations. And we're going to use the computer to discretize the system. But hopefully, what we've done today is reviewed a little bit about the origins and the measurements involved with fluid mechanics. What is your modus operandus for solving these equations? And up to this point, what do you do? Typically, what do you do in fluid mechanics? Yes? Well, you're just scratching your nose. Yes? Okay.
Tend to strike out any components that don't apply, like if the problem tells between more gravity, or if it's in viscous or inviscid, and then from there you can usually integrate it or solve it as differential equation.
Right. so what you're trying to do is eliminate terms. You get differential equations, hopefully simple ones. Then what do you do with those simple differential equations? You apply the boundary conditions, right? And then you put on the average. Okay, so that's kind of the operation that you're familiar with doing. Okay, so it's time for the finite volume method. Okay. So before we do or describe the finite volume method, let's take a step back and just again review this nice figure that describes taking a continuous system, right? So our problems have mostly involved analog systems, shall we say, right? Where satellite doesn't really just move between discrete regions. The heat doesn't really just flow between discrete regions, right? There's like continuum. And we break it up. Okay, so some things to consider are the physics that we're trying to solve. And in this case, we're going to look at the heat equation again. Even though we just talked about fluid mechanics, okay? But you'll see the analogies. The analogy between fluid flow, right, and heat flux are nice and real, and something we can see in the heat equation and Navier-Stokes. They both have this Laplacian operator, right? So we're going to set up our physics. We're going to discretize our domain and our equations, right? How do we discretize? What's kind of the easy way to discretize the partial differential equations? Finite difference, right? That's a pretty simple way to do it. Or we can use finite elements. Right now we know that method too, kind of, and use the Galerkin method. Or we can hope that a computer can do it. What do we get? We get a system of algebraic equations, and as we've talked about in the past, essentially, right, we get a K matrix, and we get a T matrix, and we have some type of forcing matrix. What we're really trying to do is set up a bunch of algebraic equations that give us a K matrix, and then we have to invert that somehow to figure out what's in the T matrix. We're doing one direction, 1D problems, is figuring out what this T column vector looks like. And then we get a solution, all right? Okay? We haven't really talked that much. We've talked mostly about setting up this K matrix and then saying, okay, in simple cases we can kind of invert the matrix, but there are other methods that are involved to be able to solve that. Okay, so here is a nice illustration from this book that says, hey, here's a domain that we have, and in this case, it's a heat transfer problem. We've kind of done this. We did this in kind of in 1D, right? We had, hey, we're going to have heat sources at every location on the interior, and we're going to have boundary conditions. We're going to have Neumann on one side, Dirichlet on the other side. So Neumann being the heat flux in, and Dirichlet being, hey, this is a fixed temperature. So in this case, they're saying, hey, this microprocessor has a fixed temperature, and this there's a heat sink over here as well. Okay, and then you can go about looking at the discretization of this domain, and we can come up with this K matrix, right? We talked about. here, sorry. You set up this K matrix like so, and we have our temperature column vector, and we have some type of forcing matrix over here. And you can kind of see, hey, look, they've got some symmetry that they're trying to impose on this system with some type, and maybe there's some, maybe this is a sparse matrix, but you have different ways of looking at it. There's not, you can see, well, there's something contributing over there. Okay, so the physics is going to revolve around the heat equation again. Okay? And if it's a steady state problem, what do we say? We said, okay, the temperature is not going to be varying as a function of time, or I mean it does, okay, but if we're looking at the steady state solution, we're looking at what happens after a long period of time and it's stopped changing. And we talked about that, remember we said if you had two insulating barriers and you have heat flux coming in, that thing's just going to keep increasing the temperature. But with a nice sink, okay, like a temperature sink at a fixed temperature, you could come up with a convergent solution. So, with this method, you can still break things up into elements. So maybe they would have called it the finite element method. I don't know, that instead of finite volume method, but this one's called the finite volume method. And in each of these elements, okay, and this is, you have an element field, all right, but what you have is a centroid and you have faces, okay? So what we're going to be thinking about is how to, let's get rid of that, all right? We have the physics. Okay, like that. And we have some Laplacian, so some second derivative that we have to take care of. And we have this element number 9 that's going to be surrounded by 9 elements, but we're really only going to be looking at what happens in element 8, 4, 10, and 15. So these are the elements that are going to be of concern for us. And if we zoom in even further here, what you see is we can label the wall on the right lowercase f1, and we can label the centroid of the neighboring element on the right capital F1, or we can label that element F1, capital F1, okay, but it has a centroid over here. And we do the same thing for these other locations. And in the finite volume method, we think of individual control volumes. Okay. So in our case, if we look at an integral form, what we have is an integral where we're going to take take two integrals of the left side and two integrals of the right side. Or we're going to take the volumetric integrals, but it's a 2D problem, so that's why we have a double integral. Okay, on a control volume for this equation, the heat equation, as we see here. Okay. Now, zooming out, all right, this is what we have. there's something called the divergence theorem. Okay? You may have used it in math, right? And so with the divergence theorem, what it says is that you can take a volumetric integral of a divergent, of something with a derivative in it, or a divergence, okay? And you can write it out in terms of a surface integral, okay? Now, note, I guess maybe, all right, I'll go ahead and I'll put dots here because that's how, just to be consistent with what I've got here, okay? Some people put dots, some people don't put dots, but since I have dots in the templated portions here, I'm gonna keep the dots, right? Either way, it's a heat flux. So the divergence theorem can say that we rewrite the expression that we just have here in terms of surface integrals on the heat equation as such, okay? For the left side. The right side, you just say, hey, I'm doing an integral of q dot dv, a volumetric integral. So this one, just, I'm going to say, hey, that's just q dot times vc. Okay? And then we can begin to discretize this surface integral by thinking about what's happening with the 4 relevant elements. This element over here doesn't have a surface, it just has a corner to act on the central element of interest. Okay? But these 4 neighboring elements that we highlighted before, those are going to be the ones that are going to be interacting with our system. So we're going to end up having 4 discrete contributions. Let's see. Yeah, good. Okay, so the equation that is of interest becomes the following. It's going to be acting on the 4 faces of interest. It's still the expression we had here, which is the integral of the Laplacian. Okay? And that is going to be acting on each of these faces, and it's essentially going to be akin to a heat flux. Okay? So we have, breaking this down, that's an S. I know, it looks like an integral. Plus okay, and this is going to be equal to the right side. Okay, so this is, we'll just say right side, which is just q dot c vc. So how do we calculate this? Okay, this SF1, all right? SF1 is going to be the height, this delta y, okay, of this face 1. Okay, so we have SF1 here with a direction in the I direction. Okay, so SF1 is a vector that's just like this. Okay, SF2 is going to be a delta x, okay, in this direction. So this is going to be delta x, f2, and it's going to be in the positive y direction. So this is going to be j hat. The surface for 3 is going to be delta y, and it's going to be in the negative direction. So we'll put the negative in front, and we'll put the I hat behind it. And similarly, SF4 will be in the negative direction, and it's in the delta x, or it's in the horizontal direction, like we have here. And this is going to be on the 4th face, and this will be in the j direction, or it's in the negative j direction. Okay, pretty straightforward so far. So now we've got our s's, whoops, these s's, this one right here, this one right here, this one right here, this here. And what we don't have is the minus k delta t. Well, how do we handle this? Let's take a look. All right, so this is the set of equations that we have, okay, and it's going to be equal to this this q dot v, and we need to think about, okay, what is this essentially this gradient of temperature on face 1, because we just have a minus k as our term. So if we think about, hey, what is the gradient of temperature across face 1, we can say, well, we could have something happening in the x direction, and we could have something in the y direction, in the j direction. Okay. And so here, okay, we can say, well, you know, there's probably, sorry, this is face 1, sorry. There's not really anything happening in the y direction on face 1. Okay, right? But there is stuff happening in the x direction. So we can say that this term could be thought of as, hey, what's the temperature at this centroid? What's the temperature at this centroid? Like that. And what is the distance? Now it's the centroid distance. It's this distance right here, okay, that we're interested in. And we could call this, what in the, all right, okay, I'm sounding like kids. Okay, right like this. Okay, that's how we define it. Okay, so this is a first difference approximation of what we have there. And we can set up, essentially, a whole bunch of rows in the K matrix that is composed of these first differences and these S terms, okay, to be able to figure out and represent the heat equation. And so you see that, you know, we have the interaction left, right, up, down. And you're like, isn't this a lot like the finite difference method? Well, yes, it is quite a bit like the finite difference method, okay? But what we're doing instead is we're thinking more in terms of what's happening with the spacing, okay? And we're thinking more about what's happening with these distances that could be varying, and we're thinking about what's happening with the flux. So it's very, very similar to finite difference, but we call it finite volume. Once we have, again, the K matrix, the T matrix, and the 4C matrix, the goal is to figure out the T matrix by taking the inverse of the K matrix in some way, okay, and multiplying it against the 4C matrix. Now, which should we use? Which method should we use? You have two choices. One method is the finite volume method. Okay. And so ANSYS, that uses Fluent, uses the finite volume method. So if you ask the ANSYS people, which method should you use? They will say the finite volume. If, all right, and so you can read about this here, okay? Yeah, so you can, and it's not, you can also compare it against the finite difference method, okay, or as well. If you ask console, they will tell you it doesn't matter. Well, actually, it does kind of matter. What they'll tell you, their argument is, I can do anything you can do using the finite element method. And so they use the finite element, all right? And they've written this little thing here saying, commercial packages for CFD are traditionally based on finite volume methods. Okay, this is due to the fact that basically all of the larger commercial packages for CFD have the same ancestors. Right? So they're saying it's hereditary. That's why we use the finite volume method. But they specialize in the finite element method. So it's just to share that you have options if you have a lot of money, or if you're poor and you want to use an open source solution, you also have options. Here is just a little bit suggesting, again, this is from COMSOL, all right, what the strengths, I guess, and applications would be for which element you would use. So finite element method, this is what COMSOL does. Says it's good for everything. Okay. It does say that finite difference does have some strengths. Okay, and astrophysics. Okay, that's great. In seismology. Okay, and I'm not quite sure how to use finite difference to model these things, but it's a possibility. And then finite volume method is rather limited. Okay, from their perspective. CFD, heat transfer, and chemical engineering. Okay. So when we use Fluent, we will use the finite volume method. I'll show you when we do some stuff with cylinders that you can also use COMSOL and show you, some results there. So much of this, though, when you start using commercial packages, is on the user interface. Okay. So much of it is. So often, you're not going to really see the difference about what we're using, but I will say that Fluent does a nice job of computing drag on surfaces and the forces. So that's kind of what I'm saying from a user interface perspective. But you already started to get some experience with ANSYS, and sometimes it isn't pretty. But we'll get through it together. All right, so that's pretty much it for today. That is it in terms of the technical content. What we did is we did not review mechanics, but we did go over outlines for the final project, and we talked about fluid mechanics, and then we discussed the finite volume method. All right, let's take attendance, and let me shut off the stuff.